Welcome to note set number 14, where we'll be talking about circuits with non-periodic sources. So again, when we say circuits, really we should be thinking about systems in general, but we'll be primarily illustrating with circuits, but we will see some examples of non-circuit ideas. And we're talking about non-periodic sources. We've already used the Fourier series to deal with periodic sources. Now we're going to use the Fourier transform to deal with non-periodic sources. But remember, the underlying idea in all of this is understanding how a single sinusoid, and in particular a complex sinusoid, goes through a linear time invariant system. And the Fourier series and the Fourier transform just provide a way of summing all those sinusoids together to create the input signal on one side, and then we figure out how those Fourier series coefficients change as they go through the system, or how the Fourier transform changes as it goes through the system. And then on the output side, the Fourier transform, technically the inverse Fourier transform, just adds up all of those components. So in the previous lecture, we talked about this convolution property, and I said, this side we're not really going to think about at all until towards the very end of the course. But it's this side, and we'll be seeing where that comes in. So remember, this is like the amplitude and phase. It's like the phasor for the signal at a particular frequency. And this will act as the modifier that changes that amplitude and phase as a result of the system. And so that's the kind of idea that we're looking at. We've seen this already for the periodic signal, where we break our input down into this sum, and we just have to focus on this kind of pseudo phasor at the frequency k omega 0. So C1 tells us the phasor magnitude and phase at the frequency omega 0. C2 tells us magnitude or amplitude and phase at the frequency of 2 omega 0, and so on. So these CKs are descriptors of the input signal. The DKs are the Fourier series coefficients of the output periodic signal. And this is the key that links them. C sub k, again, input phasor, so to speak. H evaluated at the frequency where that phasor lives tells us how it gets modified to become the output signal's phasor at that frequency. So that's for Fourier series. But notice that this structure is identical to what we're seeing up here. Input signal, let me rephrase that. Input signals Fourier transform, output signals Fourier transform, linked multiplicatively through that system that is the system's frequency response, h of omega. Down here we see the same kind of thing, except we have to evaluate it just at the discrete frequencies that we have for the periodic signal. So where does this all come from? Really? Well, you can go back and look at a linear circuit, and again, that could be thought of as linear system. E to the j omega t, complex sinusoid at frequency omega, goes in, comes out as the same frequency, just a different amplitude and phase. So it's going in here with 1 out in front, and it's coming out here with h of omega, a complex number representing magnitude and phase change from what went in. So now we're looking at this integral as being something that sums up all of these things. So we can think about how each one of these terms goes through. Each one of them goes through in exactly the same way as we had up above. So just to put a finer point on this, up above we could have some x phasor out in front, we would have the x phasor here. So that x is playing the role here and here. So that's the main idea. So again, the key thing here is this multiplicative operation. That's the beauty of going into this so-called frequency domain. Now, for the Fourier series case, let's back up. We saw that we could actually numerically compute this sum to get an approximation for the input, then numerically do this on our computer to simulate the effect of the circuit, and then numerically do this sum for some finite number of terms, and we could actually see what the output signal is going to look like. That was all doable because we're talking about discrete sums. But now here we've got an integral, and so it's not impossible, but it's not easy to do this numerically. Could do it, but it's generally not the main use of these ideas. The main use is to use this connection as a way of visualizing what the circuit's going to do by looking at the effect of this h of omega, and that's the big idea. And we can even do that visualization for the case with the Fourier series. So that's the real big idea here. So the continuing with this big picture view, we've got x of t. It gets transformed to its Fourier transform. We know how the system modifies that Fourier transform as it goes back. We then take this, put it in here, and in theory anyway, do an inverse Fourier transform to get back y of t. So that's the theory behind all this and the concept, but we rarely actually do all of that. What we mostly do, and we'll be illustrating this a lot as we go through the course, is we just simply look at, for the system, what does h of omega look like without even knowing for sure precisely what input we're going to have into our system. Maybe we're designing a circuit that's supposed to take in audio signals, guitar signals or something like that. We don't know what that guitar signal is going to look like ahead of time. There's lots of different guitar signals. But by looking at h of omega and understanding its characteristics, we can get a feeling for what it's going to do. And the main thing that we look at is the magnitude of that frequency response. Remember, h of omega is called the frequency response of the system. We put it inside this box to say it represents the characteristics of that system. So looking at the magnitude tells us how it changes the amplitudes of the input components to create the amplitudes of the output components. That's the big thing. Yeah, it does change the phase as well, but we're less interested in that overall, although we will talk about that to some degree. So this idea right here, the fact that magnitude of h of omega modifies the magnitudes or amplitudes of the input components, tells us that what the system can do is, when this value at a certain frequency is greater than 1, it's going to emphasize those frequencies by boosting how much of them we have. And at frequencies where magnitude of h of omega is less than 1, then that's going to de-emphasize those frequencies. So what we can do is look at a plot versus omega of the magnitude of h of omega, and this will be we'll have even symmetry, so I'm just going to draw one side of it. So it may do something like this, and so maybe this is 1. So what that's saying is, in this range of frequencies here, the system isn't really doing anything. It's passing those frequencies kind of untouched. But in this range of frequencies, it's suppressing or attenuating the contribution. So it's reducing the contribution of those frequencies. And by doing that, we can change the signal. And we'll talk more about this as we go. Now, let's take a look at a very real-world example with application of this. And the thing that I love about this example is not only does it bring into play this idea of frequency response, but it also helps us see how knowledge of the Fourier transform properties really helps us understand how to work real-world problems. So you may have gone to a concert at a certain venue, and you yourself may have said this, or you may have heard somebody say, "Man, the acoustics in this room are horrible." Um, and you may know that the sound engineer at that venue may be trying to fix that by using a device called a graphic equalizer. And basically what that graphic equalizer does is it implements this h of omega for a particular device that the audio signal goes through before it gets to the speakers, and we'll see more about that. And what the audio engineer might do is use the controls on this device called the graphic equalizer to boost the amount of some frequencies and to attenuate or cut the amount of other frequencies. So let's take a look at how this works. So here's a speaker over here, and here's a very large ear, or maybe it's a very small speaker. I'm not sure which of those two cases I've illustrated here. And suppose there's some reflecting surface, and so this could be like a wall or a ceiling, and we're looking at a very simple case where there's only one reflection. So the signal that we receive directly we'll call x of t. And then the signal that we receive that goes up, bounces off, say the ceiling, and comes back down to the ear, that has a longer path, so it's going to take longer to get there. So it will arrive c seconds later than x of t, and the value of c will depend upon the geometry between the speaker, the ear, and the reflecting surface. With a little trigonometry, you can figure out what that c value is. It will also arrive with a different amplitude, alpha, and we will assume alpha is greater than 0 but less than 1. So not all of the energy that comes up is reflected off the surface. Some of it will be absorbed, and how much is absorbed depends upon the particular type of surface. If it's a nice smooth hard surface, alpha will be close to 1, but if it's kind of like a sound absorbing material, like foam or something like that, then alpha might be very close to 0. So what we hear is the sum of those two signals. So we say y of t is equal to the sum of those two. And ideally we would like to just hear x of t alone. And so what we have here is a system. We have an input signal, x of t, that gets modified somehow. Delay is added to create an output signal. So we can think of this whole thing as a system. And we can analyze this using Fourier transforms. So the Fourier transform of the received signal y of t, we take the Fourier transform, use linearity to pass through. So we pass the Fourier transform through these terms, pull the alpha out in front. So we have the Fourier transform of x of t as x of omega. The Fourier transform of a delayed version of a signal, we go back to our time shift or our delay property, and so it's the original Fourier transform times this e to the minus j omega c. If you're unclear where that came from, go back and look at our lecture on the time shift property back in the Fourier transform properties lecture, or just look on the table, the Fourier transform properties table, for the time shift or delay property. So now we see we have a common x of omega in there. So we can factor that out, and lo and behold, we have this scenario that we've been talking about. This quantity here is multiplying the input Fourier transform to create an output Fourier transform. Ha! This is the h of omega, or the frequency response of the room. So we can look at this quantity, and in particular if we look at its magnitude plotted as a function of omega for different values of alpha and c, then we can see what different types of rooms will do to what we're trying to hear. So that's the basic idea. So we take the magnitude. Let me back up here. So if we want the magnitude, geez, this pen is horrid. If we take the magnitude of this, we need the magnitude of the whole thing. Magnitude of the product means product of their magnitudes, and so that's how we get to this scenario here. Again, you need to brush up if you're not very competent with your complex number manipulation. You need to get that under your belt. This will just keep happening all semester long. So we see that we've got the magnitude of h of omega, and through this multiplicative process, it's going to change the shape of x of omega. What we see out here will not be the same as the shape that we really would like to hear. So we're going to hear certain frequencies boosted and certain frequencies cut, as we'll see, but we're not quite there yet. We have to find out precisely what this thing looks like. Well, there is the structure of that, so we're going to take the magnitude of that. So yes, we could just go right into MATLAB and use the ABS command directly on this function, but it helps to be able to do some math every once in a while to see what things are going to look like. So we use Euler's formula on this E complex exponential and break it into a sine and cosine part. So now we've converted something that is in polar form here into rectangular form, and the beauty of that is that once it's in rectangular form, it's easy to add to this 1. See, the problem here is we've got something in rectangular form plus something in polar form. So adding we want to do in rectangular plus rectangular. So that's the point of doing that. And so now we can add those, and effectively that's saying this is the real part of the sum, this is the imaginary part along with the negative sign. And so to take the magnitude, we take the square root of the square of the real part plus the square of the imaginary part. Notice that you do not bring the j along, so do not bring the j. Otherwise you'll end up into trouble, or could end up in trouble, with a negative value underneath your quadratic, which would get you back to something complex or imaginary. So now we can do a little bit more algebra here. We've got a square of a sum of things, so we can expand that out and get all of this stuff. And the point of doing that is to recognize that we factor out an alpha squared, and we see that we have a trig identity that cos squared plus sine squared is equal to 1. So that whole thing just boils down to alpha squared. And so now a little bit more manipulation, and we have something that looks like this. And now that's very easy to visualize, and also very easy to plot. So if all we had was this term, h of omega would be flat. But what we see is we've got something that's constant plus a wiggle on top of it. Now that wiggle is originally sinusoidal, but then because of the square root, it kind of warps the shape of the sinusoid. But nonetheless, we still expect kind of an up and down wiggle. And as we go across omega, c kind of sets the, I hate to do this, but omega is frequency, but we're looking at this as a function of omega, and so c kind of sets the frequency in frequency. It just sets the rate at which this thing's going to wiggle up and down as we go across omega. And so this is the effect of the room on our audio signal. There's a plot of just this part, just the frequency response magnitude, for an attenuation of 0.2 and a delay of 0.5 milliseconds. And we can see a couple things. Yes, it wiggles up and down like we said, and we can actually figure out the spacing between those dips and peaks, and so we can figure that out, that it's 1 over c hertz. So I'm plotting this in f rather than omega, so I've just replaced omega by 2 pi f. That's all I've done. So up here in my equation I've replaced omega, not c, omega. I've replaced omega. Man, up in that corner it's hard to write for some reason. I don't understand why. Anyway, we replace that omega with 2 pi f, plot it versus f, and actually I'm plotting it in kilohertz. But from the math, you can figure out that the spacing between the dip-to-dip spacing or the peak-to-peak spacing is actually 2 kilohertz apart for this example, but that's 1 over c hertz. So in this case, c was half a millisecond. You take 1 over half a millisecond, and that gives you 2,000 hertz. So we can see immediately that the delay controls the spacing between the dips and peaks, and it's the alpha that sits out in front here that controls how big the dips and peaks are. So remember, alpha is how much attenuation there is, and c is the actual delay. So so let's look at these next 3 slides to see what the effect of these are. Now, just so that we can get a rough idea, what's a typical value for this delay c? We want to be looking at the right kinds of ranges for audio. So for the speed of sound in air, at least in a vacuum, it's 340 meters per second. Let's say that a typical difference, for a typical small concert venue might be something on the order of 0.2 meters, something like that. I picked 0.167 meters just so it comes out to a nice half millisecond, and that gives us a spacing of 2 kilohertz. So that tells us that this half millisecond delay is a reasonable delay, not something totally unusual. So here is the case that we just looked at, alpha equal to 0.2, delay half a millisecond. So we get our dips and peaks spaced by 2 kilohertz. So let's just imagine that maybe our signal that we want to hear, our audio spectrum, looks like this. Now, that's a made-up spectrum, but it's real audio, as we'll see in some examples later in the course, does not look like that at all. But this is a good illustrative shape to look at. And so then this is the effect of our room. And then finally we take the product of those two things, and you can see that these ups and downs will make this thing go up and down, and we do indeed see that. So so instead of hearing this spectrum, we're hearing this. Now, how, is that a big enough up and down to make the music sound horrible? Probably not. But remember, that's for a fairly small value of alpha, so that means that there's not a strong signal bouncing off the ceiling in this case. Now let's change the amount of alpha. So now we've moved to a ceiling which is much more reflective, and you probably have a good feeling for, if you've been in a room that has very reflective walls, how horrible that environment sounds. So we'll keep the delay the same, so we see the same spacing, but now we see a much larger up and down, and we see a much more pronounced effect on the spectrum. So instead of hearing this, we're hearing that. And so again, whether this is going to be a serious degradation to the audio or not, I can't really say for sure. But it is illustrating that the room is doing something bad to the signal. So again, we get this bottom one by taking the top one times the middle one to give the bottom one. That's what our theory shows us. So look at this. The beauty of this is that, yeah, we knew that reflections cause problems in a concert venue. And someone will walk in and say, wow, this room sounds horrid. Well, it's because that wall over there is reflecting, or whatever. And maybe you've seen pictures of recording studios with foam on the walls and things. But the beauty of this is it tells us what matters and why it matters, and what effect different changing different quantities will have. Without this theory, we would just be blindly searching in the dark for how this works and what we need to do and what effects things will have. So the thing that we're seeing here is that a stronger reflection causes more degradation because of larger boosts and cuts. Now let's go back to our small value of alpha, but now we're going to have 0.1 milliseconds instead of 0.5 milliseconds. So we'll have a shorter delay. And so now you'll notice that the spacing between the peaks is 10 kilohertz. So we're really only able to hear from 0 to 20. So we're really only seeing, effectively this is like just two dips. We'd be happy if everything went flat across, even if it was, that's a little bit high, higher than 1. The important thing is to have it be flat, not where the level is. And you can see that the effect on the received spectrum still gives small boosts and cuts, but they're widely spaced. Now, if you were to, I didn't do it with alpha equal to 0.8, but if you were to do it with alpha equal to 0.8, you'd see much deeper cuts and boosts like that. So now it becomes quite a serious degradation to what you're hearing. So we've learned something, that the delay affects the spacing between these dips and peaks, and that the amount of reflection affects how deep and how tall the peaks are and how deep the dips are. So two good things that we've learned here. So if you want to create those pictures, this is what the MATLAB code that I used to do that. So here's my, I'm just creating a range of frequencies, converting it into omega to work with directly with the equation. Here's my made-up fictitious audio spectrum. I just played around with some equations in MATLAB until I got a shape that looked kind of like what I wanted. And then I'm just plotting that. Here's where I create my H, and actually technically this is already the magnitude because I'm doing the absolute value of that. And you can see that I didn't use the end result of all of our algebra and trig. I just used the original result with the ABS. And then I'm just plotting that versus F, but dividing by 1,000 to get it in kilohertz. And then, of course, labeling. Everything's about labeling. So check that code out and try it out. Now, suppose we're an audio engineer and we want to try to fix the effect of this room. So we've got an amplifier here that's driving the speaker, but prior to the amplifier, we can put in, that should not be there. I've already fixed that in the notes to be posted. So we can design a system, a filter, equalizer that we put in there, such that we pre-warp x of omega before it goes to the speaker, so that ultimately, and we've talked about, if this is if this product is what's coming out, then we know that our room hits against this thing, and then plug in all of that for this, and we see that we get this triple product for this cascade of our equalizer cascaded with the room. And that's a standard result, that cascades of systems result in multiplications of their individual frequency responses. So now the idea is this. We take the magnitude of that and we get the product of three magnitudes. And so remember that we've seen that this creates dips and peaks, and what we'd like to happen is for this thing to dip when this peaks, and for our equalizer to peak when the room dips, so that the whole thing ends up being equal to 1. So here's an illustration of that. So here's the effect of the room. Here is some equalizers frequency response, and you can see that they peak and dip in opposite places, so that the product ends up being perfectly flat. And I grabbed an image here from one of my favorite websites, Musician's Friend, showing an equalizer, and you can just kind of make out that they have the sliders on that equalizer set in the kind of shape that we're talking about here. Now, technically, those sliders are on a dB scale, and we're not talking about dB yet, but we will be pretty soon. But the cool thing here is that each one of those sliders allows you to pick how much attenuation or boost occurs at the corresponding frequency. Each slider is labeled with a particular frequency, so you can kind of imagine, this is a rough generalization, but the basic idea is that the shape of the sliders that you have here outlines the shape of the frequency response of that system that you get. So, you know, an audio engineer is not going to sit down and work out all this math. They're going to tweak those knobs until it sounds right. But the really best audio engineers are the ones who understand what's going on behind those knobs and can listen and say, I hear this effect, I know what the solution to that is, and then be able to do it. So we'll be drilling these ideas in further as we go on. But again, the big idea is circuit, system, linear time invariant. Its effect in the frequency domain is multiplicative with this idea of a frequency response. That is the big, big, big idea here. Thanks. See you next time.